In this video, we're going to begin our discussion with estimating a population mean. In the last section, we did confidence intervals around the point estimate p-hat. In this section, we will work with confidence intervals using the sample mean. Remember, the goal of a statistical inference is to use information obtained from a sample and generalize the results to the population being studied. You must obtain a point estimate of the parameter first. So point estimate, it's a value of a statistic that estimates the value of a parameter. So the point estimate for the population mean is the sample mean, and the point estimate for p is p-hat. Now, the sampling distribution of the sample mean x bar. You need to have a simple random sample of size n. X bar is approximately normal if the population from which the sample is drawn is normal. That is the normal probability plot. Or the sample size is sufficiently large. That talks about the central limit theorem. Okay. The mean of x bar is equal to the population mean. The population standard deviation of x bar is the population standard deviation divided by the square root of n. Now, following the same logic from the last section, we know it's what? Point estimate plus or minus the margin of error. And that would be written as that. But we have a problem here. We need to know the population standard deviation. If we don't have the entire population, it's impossible to get the population standard deviation. So, instead of using the population standard deviation, what can we use here? Yeah, we can use the sample standard deviation. So I can rewrite this. Replace the population standard deviation with the sample standard deviation. But we have other problems. The sample standard deviation is a statistic and therefore will vary from sample to sample. Using the normal model to determine the critical value, z sub alpha divided by 2, in the margin of error does not take into account the additional variability introduced by using the sample standard deviation in place of the population standard deviation. This is not much of a problem for large samples because the variability in S decreases as the sample size increases. That's the law of large numbers. But for small samples, this is a real problem. So furthermore, the z-score is given by this particular formula, follows the normal distribution, which allows us to find the critical value. However, replacing the population standard deviation with the sample standard deviation does not follow a normal distribution. A new model must be used to determine the margin of error that accounts for the additional variability. This new model is Student's t-distribution, founded by William Gossett. Quick story about Gossett. Gossett worked for the Guinness Brewing Company. Yes, that Guinness Brewing Company. He was in charge of conducting experiments at the brewery to identify the best barley variety for new beers. He used very small batches and sets to create these new beers. The problem is Guinness would not allow Gossett to publish his results under his real name. Therefore, he chose to change his name and publish the results under Student. Okay, let's talk about Student T's distribution. Suppose that a simple random sample of size n is taken from a population. If the population from which the sample is drawn follows a normal distribution, the distribution is t equal to x bar minus mu divided by s divided by the square root of n. Follow Student's t distribution with n minus 1 degrees of freedom. X bar is a sample mean and s is a sample standard deviation. The t statistic represents the number of sample standard errors. The sample mean is from the population mean mu, and a picture is given below. On the next page, here is a t-distribution table. Now, we will not be using this in this section, but I at least wanted to show you what one would look like. So, constructing a confidence t-interval about the population mean, provided that the sample comes from a simple random sample or randomized experiment, the sample is less than or equal to 5% of the population, and either the population is normally distributed or the sample size is large enough, a 1 minus alpha times 100% confidence interval for mu is given by, so the sample mean plus or minus t sub alpha divided by 2 times the sample standard deviation divided by the square root of n, where t sub alpha divided by 2 is the critical value with n minus 1 degrees of freedom. And in this case, the margin of error is t sub alpha divided by 2 times the sample standard deviation divided by the square root of n. Note, if a data set has outliers, the confidence interval is not accurate because neither the sample mean nor the sample standard deviation is resistant to outliers. Sample data should always be inspected for serious departures from normality and for outliers, unless you have enough data values in order for that to not matter, aka the central limit theorem. That will be extremely important moving forward.